Well, today we're going to look at the applications of where we use exponential equations, or we see it quite often. Anytime that we see growth in terms of a percentage, or if we see something decreasing in terms of a percentage, that would give us a clue that we would be using an exponential model. So let's take a look first at exponential growth equations. Exponential growth equations, the basic form of an exponential growth is going to be this form. A times the base is going to be 1 plus the rate for that. Okay, now A is going to be the initial amount. It's also going to be what our y-intercept is. And remember that the rate, R, is going to just be our growth, the growth rate. So if it's increasing by a certain percentage, then we'll have that. So in many of the problems, what we're going to be looking for is the percentage increase is the rate, and again, we're going to use that as we write that as a decimal. And then we'll take whatever we start with, the initial amount, and if we want to find the future value of that amount, then we can use that. And in this case, time is usually in years. When we talk about a growth rate per year, then time is going to be in years. So if we look at the first example, notice that they say that we have an original investment of $1,800. We're going to increase that by 7% a year. So we want to write an exponential model for the situation and then find out what it is, the investment after 15 years. So the good way to start this out is just to think, okay, so what are the key components? Obviously, the initial amount is going to be 18,000, or I'm sorry, 1,800. The growth rate is going to be 7%. So we're going to write that as 0.07. And then the time, eventually, we're going to look at 15 years. So to just write out our function, we're just going to use the initial amount and the rate. And so we're going to write our 1800 multiplied by 1 plus 0.07, and then raise that to the t power. And then if we actually want to just find out what 15 years are, we can go ahead and just adjust that growth rate to, instead of writing it as 1 plus, just go ahead and write it as 1.07. So you could just type it in on your calculator this way, and we'll find that this is going to be $4,966.26. So the other basic model that we see is exponential decay, and that's when something is decreasing by a certain percentage. Now, when we write that function, notice that there will be one change. We'll still use the initial amount, but this time we'll be thinking it in terms of 1 minus the rate. So you're actually taking that rate, that growth, that decay rate, and you're subtracting it from 1. So again, A is the initial amount, R is the decay rate as a percentage, okay, written as a decimal, and then T is time. So when we think of decay rate, so for instance, in this first one, we have an investment of $12,000. It's losing value at a rate of 4% a year. We're actually going to take that 4% and subtract it from 1 to get what our decay rate is. That's going to give us the multiplying the decay factor with that. Okay, so in this case, A is our $12,000. We can do that. R is the 4%, and then obviously the time, we're looking for the value of the time in the investment after 9 years of losing 4% a year. So let's write the function first. And again, if we write the function out, we're just going to use A, the 12,000, and then we're going to do 1 minus because it's losing that rate with that. So notice that the decay factor, when we go to evaluate for 9 years, the decay factor is actually going to be 0.96, meaning that really you have 96% of the value left. So if you lose 4% of it, you have 96%. So that's what you're actually multiplying over and over again. And that's why we refer to that as the decay factor compared to the decay rate with that. So you can see that we would only have about $8,310 left with that. And again, you're just using the calculator to multiply these out to find the value. Now, the last application of when we see exponential growth happen is when we talk about in real life. We don't often have percent calculated for an entire year because when you put money in a bank or you pay a car loan or something like that, you're paying usually monthly, or or they're calculating it at some smaller period throughout the year. And this is what we refer to as compound interest. This is probably the most powerful idea when it comes to thinking about investing or being able to understand how our money can grow if it's invested. And so compound interest is really the idea that you take a certain growth rate over a year and you divide it up into smaller periods. So for instance, it might be that you accrue interest 4 times a year, or it might be monthly or daily. I believe most credit cards calculate interest. They charge you interest daily for holding a balance on your credit card. So the compound interest formula is a slight adaptation to the compound growth, the exponential growth formula, and that is, notice that we still have the initial amount, which we're actually going to call the principal, and so we're going to use P for that. And then notice that the rate now is divided by N, because that N is going to be how many times a year are you breaking it up. So R is still the interest rate, whatever you're using, but N is now the number of time periods that you have each year that you are calculating. Okay. So again, this is going to be compounded yearly, and then T is going to be how many years that happens. So when we look at interest formulas or interest situations where it's compounding a smaller period of time than yearly, we have to do 2 things. We have to, first of all, divide the rate up into those smaller periods, and then we also have to then increase the number of times. Notice that up in the exponent, it's n times t, which means that you're going to have to say, okay, instead of just doing it yearly, we're now going to do it 4 times a year. So that increases how many times we're going to multiply this growth factor over and over and over again. So let's look at the example here in number 5, where it says that Laura deposited $12,000 into an account and she earns 8% interest. How much money is she going to have at 5 years if the interest is compounded quarterly? So quarterly means that it's 4 times a year. So let's think about, first of all, let's just write out what are the key components to it. So the principal is $12,000. Her interest rate is 8%. It's compounded quarterly, so that N is 4. And then we want to know the time period after 5 years. Okay. So these are the key things we want to write down, right? P, the principal, we want to write down the interest rate, how is it compounded, and then the time. So if we use the formula here, we're going to take that 8% and we're going to divide it by 4 first. And then that's going to be what we add. So we're going to take 8% divided by 4, and that's going to be 1 plus that. And then notice that the formula here is just going to be 4 times whatever the years are. So if we look at, for instance, 5 years, we're just going to take 12,000 and then multiply it by 1.02 because that's what it is. That's the 8% divided into 4. So we do a growth factor of 1.02 now, and we raise it to the 20th power. So notice that it's 4 times a year for 5 years. That's where we get 20, right? So n times t with that. And so then, of course, that will give us a larger value. So you can see that it's 17, almost $18,000. And again, that this is the power of exponential growth. Just in 5 years, she was able to grow the account. And again, this doesn't, you're not adding any money to this. What happens is that you earn interest on the interest, right? So you make money on the money that you have just by letting the bank use your money there. Okay. Okay. So then number 6 it will do as an example as well. Notice that this is a person who takes out a 6-year loan to purchase a boat, and they have to pay 4.5% interest, right? So you can go the other way too, where if you don't have the money to purchase something, or you don't have the money to invest, obviously, if you want to buy something, you might have to go to the bank and say, hey, I need some money. And they'll say, okay, well, you're going to pay us for that privilege of using our money. So that's interest, right? So we want to know the interest is compounded monthly, and we want to know what he's going to have to pay in total over the course of the loan, the 6-year course of the loan. And again, so we'll think of the principal is $25,000, right? That's how much money he's going to take out. The interest rate is 4.5%, so we're going to have to change that to a decimal. And then it's compounded monthly, so that's going to be 12, obviously, for that. And then we want 6 as the number of years. So if we write out the formula for this, A is amount. That's why for a given time. And if we think about this, we're going to have to take the 4.5% and we divide it in 12 equal pieces, because that's monthly. And then you're going to take that 12 times however many years. In this case, it's going to be 6 years. Okay. So again, let's think about what this looks like. So then if we calculate it for 6 years, we're going to take that 25,000, and if we take the 4.5% and divide it by 12, it becomes a pretty small percentage. However, you do have to raise it then, because 6 times 12 is 72. You have to raise it to the 72nd power. So here's what ultimately he will have to pay back. This is why it's so popular for banks and car dealerships and things like that to offer to do monthly payments, because notice that for the right to purchase something for $25,000, he's going to have to pay the bank back $32,000, which means that the bank earns about $8,000 of interest. That's pretty good money over 6 years to get back $8,000 for the choice of just doing that. So, and this is approximately how most interest is calculated for purchasing things. It's a little bit different. You might not get charged as much interest. They do a little bit of a calculation because as you pay things off, ultimately there's less. You owe less on the loan. But for simplicity's sake, this is a pretty good understanding of what compound interest, the impact of it. So you'll see a few problems like that today, and hopefully it's a good application for you.